In this video, we're going to take a look at analyzing rational functions and their graphs. So we'll look at things like domain, removable discontinuities, vertical asymptotes, X-intercepts, and we're going to take a brief look at horizontal asymptotes and even slant asymptotes. First, let's recognize the form that we want to look at for rational functions. First of all, it will be factored form. And things I want you to be able to see is we're going to follow some steps here. We're always going to find the domain restrictions first. And that will come from the zeros of the denominator. So we'll get them from there. Next thing we're going to look for is removable discontinuities. That's going to be when there's a common factor in the numerator and denominator. That will lead us to those. Vertical asymptotes will also come from the denominator. They'll be the remaining zeros. The X-intercepts will be the remaining zeros of the numerator. The Y-intercept we'll get simply by substituting in 0 for x. And the horizontal asymptotes are when we're going to compare the degree of the numerator to the degree of the denominator. So let's go ahead and take a look at 6 different examples and go through these steps the same way. So recognize there's nothing for us to factor here, so we can just jump right in and look at the zeros of everything. So the first thing we said we're going to look at is the domain. So I said we'll look at domain restrictions. That'll be the zeros of the denominator. So we simply write x minus 3 cannot equal 0, so x cannot equal 3. So I'm simply going to write it as x cannot equal 3. Naturally, you can do interval notation, you can do set builder, you can get a little fancier, but that'll do for us for now. Next thing we're going to do is see if there's any holes. So holes, or removable discontinuity, is when there's a common factor that cancels. And there's nothing here, so we can just simply put NA, not applicable. Next up will be vertical asymptotes. Vertical asymptotes will be the zeros of the denominator after it's been simplified from holes, but there are no holes. So it's simply going to be the same thing as the domain restriction. It's going to be x equals 3. Now right away, if you want, you could jump over to your graph and say, all right, at x equals 3, there's going to be a vertical asymptote, so we can put that there. That's going to be like a little guideline for us when we're making our graph. Next up, X-intercepts. X-intercepts are the zeros of the numerator. So we can go ahead and write 4x minus 8 equals 0. We can factor out a 4 if we really wanted to. We'll add 8 and divide by 4, so we'll get x equals 2. So we'll have x equals 2 as our x-intercept, or we can write 2 comma 0. Let's go over to our graph and we'll just go ahead and put it on there. Y-intercept, I said we'd get that when we substitute in 0. Another thing you can do is you'll notice when it's in factored form or original form, if you just substitute in 0, you can think about it and see you're going to be left with negative 8 over negative 3. I'll go ahead and multiply it out right now. So you'd have 4 times 0 minus 8 over 0 minus 3. They go to 0, so we get 8 thirds. Or we can say that's 2 and 2 thirds. So our y-intercept is y equals 2 and 2 thirds, or 0, 2 and 2 thirds, which we'll say is right about there. Now the last thing we said we're going to look at is the horizontal asymptote. Now for the horizontal asymptote, that's when we just compare the degrees. Now notice the highest degree of the numerator is 4x, and the highest degree term of the denominator is x. So really what we have is, in the long run, the 4x and the x are going to be what matters. The x's will cancel, so we're going to be left with y equals 4 as our horizontal asymptote. So notice, the degrees are the same. They're both to the first degree. In the long run, the 8 and the 3 don't make much of a difference. So we're going to go ahead and put in y equals 4 here. Oop. Let's make sure it's at the right value. Y equals 4. And now we have our guidelines to sketch our graph. And when you're sketching the graph, realize you're basically connecting the points, or connect the dots, and you're going to follow the asymptotes. So we're going to go to the x-intercept to the y-intercept, and it's just going to follow that asymptote. And same thing down here. Now typically, you're going to have what's called a pole at the vertical asymptotes. So if it's going down on one side, it'll be up on the other, and there'll be a little bit of symmetry there from the base graph. Now this won't always be the case. If you look at some other problems, you're going to notice if there's an even multiplicity, you're going to have them going in the same direction. And if we come across that, we'll take a look. Example number 2. Example number 2 is a little unique. Before we even get started, notice that there's a monomial denominator, just 2x, so we can actually distribute that to both. But let's hold off for a minute and let's go ahead and factor. So this can factor 2x out of the numerator. That leaves us with x minus 2, and our denominator is 2x, so right away we can see that 2x cancels out. So we said we needed to identify the domain first though, so we don't want to lose sight of that. So our domain, you'll notice, is the 0 of the denominator, so we'd say 2x cannot equal 0, so x cannot equal 0, so our domain restriction is x not equal to 0. The whole is whatever canceled out. So notice 2x canceled out. And when 2x canceled out, that led us to this new equation, which is simply y equals x minus 2. And it's linear, but we have the restriction where x cannot equal 0. So what we do to find the y value of the whole is we plug this 0 into the simplified version. So we get y equals 0 minus 2, which equals negative 2. So the whole isn't just an x coordinate, it's an xy, okay? So we'll have the point 0, negative 2. So if there's a whole at 0, negative 2, you'll notice that means there is no y-intercept, so don't get fooled by that. And we'll continue down our list. Vertical asymptote, there are no more zeros of the denominator, so there are none. So we can put NA or we can put none. The x-intercept is the 0 of the numerator, or we just have y equals x minus 2. We can say x minus 2 equals 0, so x will equal 2 is our x-intercept. We will notice something else interesting. The y-intercept, again, we're not going to get fooled and just say x minus 2 and we're going to have negative 2 because we notice there's a whole. So let's circle back to that and just say there is none. Horizontal asymptote. What I want you to notice is there's none here either. So in this case, from the original, we can get it from the original problem. If you look at the highest degree term of the numerator, 2x squared, compared to the denominator, 2x. In the long run, it'll behave like 2x squared over 2x. 2's will cancel. X squared over x simplifies to just x. So as x gets very large, the values are still going to get very large. So this is going to be y equals x. So we can say there's going to be a slant asymptote, which you'll notice in a minute, but for now, we're going to write there is no horizontal asymptote. So this really is a graph of y equals x minus 2, where x cannot equal 0. So that's just a linear equation. So we'd have negative 2, and we have a slope of up 1 over 1, and it just follows. So we'll get something that looks like this. Draw that a little bit better, and continue down like that. So we have a line with a hole. Example number 3. So number 3 is not in factored form, so let's go ahead and take care of that right away. So we'll have difference of squares for the numerator. We'll notice it's x minus 4 times x plus 4. Our denominator is some basic factoring as well, so we'll recognize it comes from the idea of reverse FOIL. Adds to 5, multiplies to 4, so that would be 1 and 4, both positive. And now let's go ahead and go through our steps. So we have the domain. So the zeros of the denominator. Right away, I'm just going to write down here, x cannot equal negative 1 and x cannot equal negative 4. So there's our domain. We have our zeros. Negative 1, negative 4. Now next up are the wholes, our removable discontinuity. Notice that x plus 4 is common to both. That cancels out. So that means there is a whole at x equals negative 4, the 0 of what canceled out. So our new simplified equation is y equals x minus 4 over x plus 1 with the condition that x cannot equal negative 4. And we can use this going through just knowing that x can't equal negative 4. But now, don't forget, we need our y value. So what does the y value equal? Well, we would take that negative 4 and substitute in to find it. So we get y equals negative 4 minus 4 over negative 4 plus 1. We get negative 8 over negative 3, or 2 2/3. Now we can go ahead and put that hole in there to make sure we don't do anything with it. So 1, 2, 3, 4, and we're going to go up 1, 2, and about 2/3, so there should be a hole there. Next up, vertical asymptotes, the remaining zeros. Well, the only zero that's left, remember we're using this new equation here, 0 of that would be x equals -1. And you will notice that the two domain restrictions will match up your whole and your vertical asymptote, the x values there. Our x-intercept will be the 0 of the numerator. Notice it's not at -4, there's just one at +4. So we'll have x equals 4. We can go ahead and put that on, 1, 2, 3, 4, and put a little point there. And I'll go backtrack and put in our vertical asymptote, which is at -1. Now let's see if we can find our y-intercept. Now again, I'm going to go back to my new simplified version. So for my y-intercept, we'll have y equals 0 minus 4 over 0 plus 1, which is simply -4. So let's go down here, 1, 2, 3, 4, and we have a point. And then the horizontal asymptote, let's see what we have here. The degree of the numerator is x squared and the denominator is x squared. So if we simplify that, because again, in the long run, the lower degrees won't mean as much, and we won't notice them. So we'll have y equals x squared over x squared, which is simply y equals 1. So let's go ahead and put that guideline in of y equals 1. And now we can simply play connect the dots or follow your asymptote. So we have our y-intercept coming up to our x-intercept, probably a little more curved than that. Not a great job there on my part. And then down to the asymptote. And again, it's going to come up and they'll behave like a pole. We'll have some symmetry. Come down, there is a hole there, and it will go like that. And our graph looks something like that, but we have all the features as well. Example number 4. Again, step 1, let's factor this. So our numerator, we could just factor out a 2, leaving us with 2 times the quantity x minus 5. Our denominator, again, some basic factoring here. We have xx, adds to -7, multiplies to +10, so we can say -5 minus 2. And yes, you'll notice right away we will have a hole. But again, let's follow our steps. Step 1, we'll go ahead and identify that domain restrictions. So we can see that the zeros would be x equals 5 and x equals 2. For our domain, we'll say they can't equal those. So x is not equal to 2 and x is not equal to 5. Next up, our whole locations. So we have that x minus 5 canceling out with that x minus 5, simplifying to simply 2 over x minus 2. But x cannot equal 5. So our whole, again, I'm going to write this one as a point. We've identified it as the 5 canceling out. So now we know we have to go and find that y value. So we're going to go ahead and substitute that 5 back in. And we'd have 2 over 5 minus 2, or 2 over 3. And that is our y value of our whole is simply 2/3. So let's go ahead and put that in. 1, 2, 3, 4, 5, up 2/3, and we're going to have a whole. We'll open circle there. Next up, vertical asymptotes. The remaining zeros of our denominator. So let me rewrite the simplified version here for you. 2 over x minus 2. It's simply 2. So it's x equals 2. Let's go ahead and put that in. Next up, x-intercepts. Now at first glance, we might think it's 5, but remember there was a hole there, so there is no x-intercept there. There is no remaining 0 of the numerator, so the x-intercept, there are no x-intercepts. Our y-intercept, we'll simply substitute in 0 to our simplified equation. So it would be y equals 2 over 0 minus 2, which is 2 over -2, or -1. So we have y equals -1, which is here. Now we're left with our horizontal asymptote. Now in this case, again, we can do the simplified version or the original. I'm going to go with the original. We had 2x as our highest degree term, and here we have x squared. So if we write that down, we have y equals 2x over x squared. An x term cancels out, and we're left with 2 over x. Now as x gets very large, which is how we look at asymptotes, in other words, we're having x go to infinity, this approaches 0. So our asymptote is going to be y equals 0. And the same thing will happen if we look to negative infinity. So we'll go ahead and put that in here. We have this line going across. And now we're going to do the same thing. Since there are no points to connect because we're kind of trapped inside the asymptotes here, this one goes towards infinity. This one is going to curl up. And again, we're going to have the same idea of having a pole here. And this just looks like a shifted version of the graph y equals 1 over x, which is another way for us to look at it. Example 5. This one's going to be a little bit different. Again, nothing to factor here. So let's go ahead and look at our first step. So notice that our denominator does not factor. And also notice that if we try to say x squared plus 4 equals 0, there's no real solution. So there are no zeros of the denominator. No real solution. So for our domain, if the denominator is never 0, we can say simply that x is an element of all real numbers, or for you interval notation people out there, negative infinity to infinity. Step 2, vertical asymptote. Well, if the denominator can never equal 0, well, there are no vertical asymptotes, so none. Step 3, X-intercepts, the zeros of our numerator. So 2x plus 1 equals 0. If we solve that, we get x equals negative 1/2. Finally, something to put on our graph. So negative 1/2, we have a point. Step 4, let's go ahead and look at our y-intercept. And for our y-intercept, if we substitute in 0, we have y equals 2 times 0 plus 1 over 0 squared plus 4. So basically, we get 1/4. And you'll notice that I did skip over the idea of a hole because there was no factor, so that there was no reason to put a hole. But let me just go back and mark that for you. So there was no holes. All right, let's go ahead and make note of that. Step 5 for us for this case, horizontal asymptotes. In this case, the degree of the numerator is 2x, and our denominator is x squared. So very similar, y equals 2x over x squared. We're going to have an x cancel out, leaving us with 2 over x. So remember, as x gets very large or very negative, it's going to approach 2 over a very large number, which essentially is going to be 0. So it's approaching y equals 0. That's the idea of limits. So let's go ahead and put this horizontal asymptote in. And it's okay that there's an x-intercept on the horizontal asymptote. So it's actually glad that that happened for this problem. And then the y-intercept is 1/4, which is right here. Now there's no vertical asymptote, so this one's kind of strange. You might say we need some calculus to figure some of this out, or you can always go back if you get stuck. You can do a table of values and substitute points, but things I want you to realize, we're just going to do a rough sketch here. These 2 points will connect, and again, we can cross a horizontal asymptote. It's a vertical asymptote we can't cross. And at some point, it's going to have to come back down to approach that horizontal asymptote. And the same thing will happen over here. It's going to come back up to approach that horizontal asymptote. But again, without calculus or substituting in more points, we're not going to have anything. Most important piece of work is done. It's analyzing. Example 6. We're going to do a few things with this one. And the first thing we're going to do is factor, like we always do. So on the top, it's quite simple. It's what multiplies to -4. That adds to -3. So we'll have -4 and +1. And our denominator is left at x minus 2. So first thing as usual, we'll look at our domain restriction, the 0 of the denominator. So we know that x minus 2 cannot be 0. So x cannot be 2. Holes, nothing was common to both the numerator and denominator in terms of factors, so there are none. We have our vertical asymptote, the remaining 0 of the denominator, which is simply x equals 2. Let's go ahead and put that in, x equals 2, our vertical asymptote. Our x-intercepts, we can see we have 2 of those. There's 2 zeros. We have at x minus 4 equals 0, so x equals 4, and x plus 1 equals 0, so x equals -1. So we have 4 and -1. Let's go ahead and put those on it. -1 and 2, 3, 4. Next up is our y-intercept. And in this case, let's go ahead and look at the original function. So if we've substituted in 0, the x terms are gone. So another way to find the y-intercept, it's just the constants of the original equation. So we'd have y equals -4 over -2, which is simply y equals 2. So we can go ahead and put that in. And now for a horizontal asymptote. In this case, we're going to look at, again, the leading term, highest degree term of numerator and denominator. So we'd have y equals x squared over x, which is simply x. So as x approaches infinity, it also approaches infinity. So we're not approaching a single value, so there is none. And we're going to do something special with this before we go ahead and try to connect these dots because we don't have enough guidance. Let's go ahead and write this equation down again, and we're going to see what it actually means. X squared minus 3x minus 4 over x minus 2. So you should recognize this is actually a division problem. So let's go ahead and divide. And we can use synthetic division in this case, so we'll use x equals 2. Remember the 0 over our denominator. And we can say there's a 1 here, and we can go ahead and set up our coefficient row if you know synthetic division. And we will bring down, multiply by 2, and add -1, multiply by 2, and add, and get -6. So when we divide, we're going to drop a degree, so this is going to end up being x minus 1, and our remainder is -6. So we can say -6 over x minus 2. That's really what y equals. So let me write this again for you. Y equals x minus 1 plus our remainder, or we can say minus our remainder, of 6 over x minus 2. Now you will notice that if you look at just y equals x minus 1, as x gets very large, this little piece over here, 6 over x minus 2, won't make much of a difference. So this is what we call our slant asymptote, is the y equals x minus 1. Let's go ahead and put that on the graph. So we will have -1 here, and a slope of 1, so up 1 over 1, up 1 over 1. So we can go ahead and put that on there. I'll put it as points or dots. Let's go ahead and put that here. So this is our slant asymptote. It's actually the line y equals x minus 1. Now let's go ahead and connect our points. Now we're going to come down here and we're going to approach that slant asymptote here. And here we're going to approach that vertical asymptote. And then this point is going to do the same thing. It's going to approach one asymptote from one side and the other asymptote from the other. And that is your introduction to slant asymptotes. Just divide and ignore the remainder. So hope that helped for rational functions.